Hello, my name is David Nori, and for my design project I'm looking at control systems. I'm trying to design a useful user interface for a spring mass damper system in Unity. Now, I'm using an online reference of a second order system implemented in Unity. As you see here is the video, a link to the video made by Tessellator about how to use math to make animations, basically. Here you have the equation of motion, which he implemented. It's a second order system because it's using the first and second derivative of position or displacement, which is velocity and acceleration. Right. So the system I'm taking inspiration from and that I'm trying to recreate is an underdamped system that can also anticipate the motion. Yes, and also I recommend for anyone who's watching this, if they want to get a better understanding of concepts in both 3D animation and control engineering, I'd suggest watching the video that I'm taking inspiration from, since it explains some core concepts related to the subject very well. So here's my prototype, my first prototype, and has no overshoot or anticipation. It's following the input 1 to 1. Y is equals to x. So instead of having this velocity and acceleration that gets affected by gains, the k values here and all that, we don't have that. We just have y is equals x, but it's still following. Here's the model I made in MATlab. The desired model that I want, the desired step response. Basically, step response being a reaction to a step curve as an input, starting at 0 before the curve starts here and going up to 1. So here's the UI that I designed. It's very busy, and unless you've worked in control animation, it's quite cryptic and you don't really know how to handle it. So you can expand here by clicking the info button here, and then you get information on what happens if you put these axes, the poles, in certain areas. Right, if you put it on this right hand side plane, then the value grows up to grow to infinity and becomes unstable, and here it decreases down to your input, so it's stable, and then it oscillates if you go in any of these on the y-axis here, the imaginary axis it's called. You'll see in a later slide. And here is the step response down here, as we saw in this slide as well. Here's basically a step response graph. Right. So pole zero placement. Zeros are shown here as zeros or O's, circles. And it's on the right hand side plane here in my model, so to get the anticipation for the motion, but it's usually avoided. This I found out later, that it's basically a kind of pole, so in some certain situations the value will grow up to infinity as well, or well, it will have problems here similar to poles, so it's usually avoided and has to be cancelled out if you want to use it somehow, but it is possible. It's just usually avoided. So poles are marked as axis, the blue axis here in the pole plot, the pole zero map, and they're staying off of the imaginary axis, just 0 here, they're not nothing here, and it's just 2 of them because it's a second order system, so it's just 2 of them. If you increase the amount of poles, then it's a third order system, fourth order, higher order system than a second order system, right? So there's something called the insignificant pole, which is the one to the left here, and the dominant pole, which is the one in the middle here, and it's close to near a value of 0. And I use this insignificant pole here to the left to increase or decrease the value, making it more strong and faster or slower by getting it closer to the other pole here, I believe. So the drawbacks of this is that it's somewhat unintuitive, the pole zero placement. So I'm looking at other improvements other options basically to go about this, right? There's also something called the unit circle here, the circle here. You should stay within that because it's a discrete system, basically meaning that, well, if you're working on a computer, you're usually working with discrete systems because it cannot, yeah, basically deal with infinity and such. This is a simplified explanation. Anyway, so why not put something on the right hand side plane? As I explained before, it's kind of a pole, so it doesn't work. But I'm gonna skip through this because there's no time. It's gonna drag on for way too long. So the other solution that I looked on to implement easier into Unity and have a more intuitive way of making a UI that's intuitive to the user, basically, is using a PID controller. PID is an acronym for Proportional Integral Derivative Control. So the proportional part being representative of the present, and then integral being the past, as the area underneath the curve, if you know what an integral is, and derivative being the prediction of the future, being the slope of the curve at that point in time of the, yeah, anyway. And we're controlling the speed here, right, of the, and the we want to get the position of our sphere to follow the input x position. So we want our output y position to follow that, right, in a certain way. So by increasing this values of p, I, and d, we're affecting yeah, basically the present, past, and future. So you should definitely check out this video. I think it's a little bit long for me to explain here. It's by it's a video put up by MATlab. I forgot the name now of the guy who made it. I think it was Bill. Was it? No. Brian Douglas. All right. Sorry about that, Brian. Anyway, check it out. It definitely explains this whole idea. So this is a P controller, basically only affecting the present. So check it out. It even has Korean subtitles. Right. So this is my current prototype of the PID controller in Unity, where the sphere with the wireframe, the X sphere, is controlled, and then the Y sphere is the system responding to the input that we're controlling, right, directly. And if you change the D value, then the sphere slows in as it's getting closer, and anticipating that it's getting closer, right? And then the P value is making the sphere move faster as it's further away, eventually getting to the input value, right, to match it. So as it was quite just trial and error to use a PID system, like the tuning that I did there, changing the values, is quite unintuitive. So it's just, it could work, just a lot of trial and error. But I went back to the previous system with the pulse placement system here, the full state feedback, as they call it, because it's a loop, closed loop. Anyway, it's the same idea with the LQR system, the linear quadratic regulator system, I guess you could call it. Basically the same idea, using matrices as well. I didn't explain that before, but it's using matrices, and it's far more intuitive than using, like, putting out pole locations for your system. And instead, it still does the pole placement kind of, but with the two values that you're basically saying how important, how much does performance cost for you, and how much does cost to you, and then you put them together as a summed value, like for cost, basically. Yeah, so let's say I'm doing a recap here of a video. Same guy, Brian Douglas. Great video, just check it out. Say that you're at home and you want to get to work. What is the optimal way to get to work? Our system basically works in this way. So we start like this, right? Is it the best way to take the car, the bicycle, or the bus, or even a helicopter, right? What's the best way? Well, here you see, if we go after time, then the helicopter is definitely the best. Oh wait, look at the cost. Well, if you have oceans of money, like if you have so much money that you can spend however you want, then of course the helicopter is the best way, right? Time is more of the essence for you. Now, if you're a student, then money is quite important to you. Maybe you don't have any money to use, so you use the bicycle. Maybe you have more time, right? So that's the cheapest for you. That's cost the least for you. But if you put them together, then either the car or the bus becomes the best option. It costs the least for you, right? So here we see, if we put together time and money together, we multiply these two values with Q and R to basically weigh them heavier or lighter, basically. So they cost more or less depending on the weight you put on them. So a weight of 1 would mean both of them are somewhat of cost something to you, right? So they're both important. So you see both the bike and the helicopter here are quite costly. But yeah, if you then put the higher value on time, then yeah, the highest cost would be the bicycle, right? And here we see the helicopter that skyrocketed up in cost, right? So, and here's another version. If you just change these weightings, it's a little bit more intuitive how it will affect the system. Basically, it will go with the cheapest option. So this is the simplest version I could find. It's still quite complex though to implement, and I need more time to research it. But it's a lot more intuitive, but still not so clear on how I could control anticipation with this. So as I said, I need to research it a bit more. Thank you. That's all for me.